Electric field, part 5. We're going to talk about the field lines and the electric spectrum. A field line is a directed curve such that the electric field vector is tangent at all its points. This is a field line that is directed in this way. If we want to draw the electric field vector at this point, we draw the vector tangent to this curve and directed in the same direction as the curve. Similarly, we draw the electric field vectors here and here. Now, what about the electric spectrum? The electric spectrum is the set of two or more field lines. Here we have a set of 3 field lines. Together, all these field lines form an electric spectrum. Here we have 2 electric spectra. In this region, we have 3 field lines. This spectrum is formed of 3 field lines. This spectrum is formed of 4. The tighter the field lines are, the greater the magnitude of the electric field is. If you want to compare the magnitude of E prime to that of E, we notice that E prime is greater than E. Let's study some particular electric spectra. Let's start by the electric spectrum of a positive punctual charge. This is the positive charge. If we choose a point here, this point is in the electric field created by this charge. Let's represent the electric field vector here. This is the electric field vector. Similarly, at this point, this is the electric field. At this point as well, this is the electric field vector. At this point as well. Here as well, this is the electric field vector. Also at this point. Again at this point. This is the field line. The electric field vector at all of its points is tangent to the field line. The field line is in this direction. Here's another field line oriented in this direction. Also, this is another field line oriented in this direction. Here as well. This is also a field line oriented in this direction. This is a field line oriented in this direction. All these field lines form the electric spectrum of this charge. The electric spectrum of this charge is the set of concentric semi-straight lines centered at the charge and oriented away from the charge. Similarly, we can verify that all the field lines here, here, and here are oriented like this. Each field line is a semi-straight line oriented towards the charge Q. It is the set of concentric semi-straight lines whose center is Q and oriented towards Q. Here we want to determine the electric spectrum of 2 charged plates. At this point, the electric field vector is perpendicular to the plates and is oriented from the positive plate to the negative one. This is E. Similarly, this is E. Similarly, this is E. Each of these parallel lines is called a field line. The set of all the field lines is called the electric spectrum between the two charged plates. It is the set of parallel segments oriented from the positive plate to the negative one. The parallelism of these field lines implies that the electric field vector is constant. The field vector E is constant. The tighter the field lines are, the greater the magnitude of E is. Let's observe experimentally a materialization of the electric spectrum between two charged plates. The experiment contains a beaker with two parallel plates in which we put some oil in it. The plates are separated by a certain distance. The plates are connected to a DC generator of 5,000 volts. We're going to sprinkle some semolina grains between the two parallel plates. When turning the generator on, let's observe what happens. The semolina grains will start arranging according to the field lines. The field lines which are perpendicular to the plates. Let's sprinkle some more semolina grains. The semolina grains will become arranged in a way that they become perpendicular to the plates. Let's stir them a little. Notice how the semolina grains will distribute along the field lines. This distribution of the semolina grains materializes the field lines. Let's add some more grains. We notice that the grains distribute according to the field lines and become perpendicular to the plates. The semolina grains will distribute along perpendicular lines to the plates. Interpretation. In this illustration, consider a semolina grain at the surface of oil and between the two parallel conducting plates. When the plates are subjected to an electric voltage, an electric field E appears between the plates. The electric forces F- and F+ act respectively on the negative charge, the electrons, and the positive charge, the proton. the electrons will move inside the grain and reach its extremity. An opposite charge will accumulate on the opposite side of the grain. At the extremities of the grain, the electric forces F- and F+ constitute a force couple that is capable of rotating the grain around its center to reach equilibrium in the direction of the electric field E. According to this interpretation, the semolina grains will be arranged on a line that is perpendicular to the plates, materializing the electric spectrum between the plates. Let's dip a conducting rod in oil and connect the rod to the negative pole of the generator, and the positive pole will be connected to the ground. We're going to sprinkle some semolina grains on the surface of the oil. When powering the generator, the grains will approach the rod since the rod is negatively charged. It is clear that the grains will align on straight lines passing through the rod. This is similar to the electric spectrum of a punctual charge. The punctual charge has the field lines of its spectrum being concentric and passing through the punctual charge. We can clearly see that the semolina grains will be arranged on lines that are concentric with the point of contact of the rod with oil. Let's add some more grains to see it better. Now we're going to determine the work of the electric force acting on a punctual charge when the punctual charge is placed in a certain electric field. Let's consider a simple case. The punctual charge is moving in the electric field created by two parallel charged plates. The plates are separated by a distance d. The plates are subjected to a voltage UAB. When the charge is placed between these plates, it will be subjected to an electric force F, which is equal to Q times E. Let's assume that Q is positive. The force F to which the charge is subjected is parallel and has the same direction as E. Since F and E are proportional vectors, hence parallel, also Q is positive, so they have the same directions. E is the electric field between the two plates. The magnitude of E is given by the formula UAB over D. The vector E is constant. Q is constant. As a result, F is a constant force. The work of F, which is a constant force, when Q moves from M to N, is given by F dot Mn, scalar product of F and Mn. F is equal to QE dot Mn. Let's now determine the expression of the work done by F. We'll do that by decomposing Mn into two vectors, Mi and In, such that the triangle MIN is right at I. So we write QE dot. Replace Mn by Mi plus In. When expanding, Qi dot Mi plus QE dot In. But notice that Mi is perpendicular to E. Hence, this scalar product is 0. So we obtain QE dot In. The work of F when its point of application moves from M to N is Q. What is the scalar product of two vectors? It is the magnitude of the first vector multiplied by the magnitude of the second vector multiplied by cosine of the angle between these two vectors. Cosine of the angle between E and In. Note that E and In have the same direction, and as a result, the angle between them is 0. Q. E is UAB over D times In is equal to D, the distance. Hence, by simplifying D, we obtain Q times UAB. But the voltage between A and B is equal to that between M and N. So we obtain QUMN. This is the work of the force F when its point of application moves from M to N. This formula is directly applicable. No matter what situation the punctual charge is found in. The work of the electric force that is applied on a punctual charge when it moves from point M to N is always equal to Q times UMN, the amount of charge multiplied by the voltage between the points M and N. This is a general formula. Now let's solve an application. We have two charged parallel plates. The voltage between the plates is 100 volts. A charge Q1 is moving from point M to point N. The charge Q1 is equal to 10 exponent minus 10 coulombs. Another charge Q2 is moving from point J to point I. We need to find the work of the electric force acting on Q1 when it moves from M to N. The work of the electric force is Q1 multiplied by UMN. UMN is the voltage UAB. Q1 is equal to 10 exponent minus 10 coulombs, multiplied by UAB, which is equal to 100 volts, and the result is 10 exponent minus 8 joules. The work of the force F2 acting on Q2 when it moves from J to I is equal to Q2 multiplied by the voltage UGI. UJI is the voltage UBA. So the charge is equal to minus 6 times 10 exponent minus 12 coulombs multiplied by minus 100 volts. UAB is 100 volts, hence UBA is equal to minus 100 volts. The result is equal to 6 times 10 exponent minus 10 joules. Note that both works are positive, hence they are motive works. In the second application, we have two parallel plates separated by a certain distance. The plates are subjected to a voltage UAB equals to 120 volts. An electron exits plate B from point M without initial speed. The electron moves under the action of an electric force towards plate A. The charge of the electron is minus 1.6 times 10 exponent minus 19 coulombs. E is the elementary charge. That is to say, its value is 1.6 times 10 exponent minus 19 coulombs. The electron's mass is given by 9.1 times 10 exponent minus 31 kilograms. In part A, we need to calculate the work of the electric force acting on the electron when it moves from M to N. Applying the formula, the work of the electric force applied on the electron when it moves from point M to point N is given by Q times UMN. Q is the electron's charge. UMN is UBA. UBA. The electron's charge is minus 1.6 times 10 exponent minus 19 coulombs. We have UAB 120 volts, hence UBA is equal to minus 120 volts. Minus 120 volts. As a result, the work of the force F between M and N is equal to 1.92 times 10 exponent minus 17 joules. This is the work of the electric force applied on the electron when it moves from M to N. Part B. The electron leaves plate B with a negligible speed. Determine its speed at the instant of its impact with plate A at point N. When it reaches point A at point N. The electron leaves plate B without speed. That is to say, the speed of the electron as it leaves B at M is approximately 0. How much is the speed V at N? We use the kinetic energy theorem. The kinetic energy theorem will be applied on the electron. The system is the electron. What are the forces acting on the electron? The electron is found in the electric field created by the plates. This is the electric field created by the plates. The electron is a charge. Hence, a charge placed in an electric field will be subjected to an electric force. Let's call this force F. F is the electric force. The electron is subjected to an electric force F. The second force is mg, which is the weight of the electron. But the weight of the electron is negligible. This is given in the question. Hence, the only force acting on the electron is the electric force. The kinetic energy theorem says that the variation in the electron's kinetic energy when it moves from point M to point N is equal to the sum of the work of the forces acting on the electron when it moves from M to N. Then delta KE is the final kinetic energy, or the electron's kinetic energy at N, minus the electron's kinetic energy at M. This is equal to the work of F between M and N. The weight is negligible. The speed at M is 0. Hence, the kinetic energy at M is 0. The final kinetic energy is equal to half m of the electron multiplied by v squared at n. This is equal to the work of F from m to n. The speed at n is equal to 2 times the work of F over the mass of the electron under the square root. This is equal to the square root of 2 times 1.92 times 10 exponent minus 17 over the mass of the electron, which is 9.1 multiplied by 10 exponent minus 31. The speed of impact of the electron with plate A is approximately 6.5 times 10 exponent 6 meters per second. The speed of this particle is very large, but it is accepted since it is less than the speed of light, which is equal to 3 times 10 exponent 8 meters per second.